Today I'm going to be talking about machine learning aided experimental design for P1. So on the first day of Futini, she showed P1 shortly, and this inspired me to do a little overview of what we are doing. So for all of you, this is the current plan of the P1 Pacific Ocean Neutrino experiment. So this is a preliminary graphic on the left. So the current plan is to put 7 clusters of 10 lines with a varying number of modules, roughly 2.6 kilometers below the water. And this all is planned to be in front of the coast of Canada with the Ocean Networks Canada. So there's the Cascadia Basin. Yeah, it's quite a nice infrastructure they have there. So it's a cabled observatory. They have a quite vast budget, and they have all the deployment infrastructure already there. And coming now from this, I will be heading over to what motivates us to do machine learning in general. So as you might know that in IceCube, there have been great advances using machine learning because it just extends the parameter space, and you can really do way better classification, way better analyzation, and you can just pretty much enhance the power of the already existing data. And this goes for triggering, reconstruction, simulation, or analysis. And up here, I put like a demonstration of the data pipeline. So it starts with the raw signal, then there's some pre-processing, and then you have basically 2 parts, which I will be focusing on here. So this is the triggering and the reconstruction. And then afterwards, there comes the analysis. So as this is a planned detector, at the moment, we've built our optimization workflow, which is totally simulation-based. So we first start with a photon surrogate model, which at the end generates our detector response. So we put a detector in, and we have this photon propagation model, which then generates us individual hits at the PMTs of the detector. And then we have the trigger model, which is my master thesis. And then based on that, we can do some reconstruction and some resolution. So if we are looking now, this is the optimization workflow, but when building a detector, what can we actually optimize? And so this is spread up in 4 dimensions. So we have the hardware, so the PMT properties, and how to calibrate the different modules. We have the algorithms, so the more efficient the trigger is, the better we can save the data that we need. And for radar west, we have the geometry. So do we want hexagonal like we have an IceCube? Do we want triangular? What's the spacing of the modules? And obviously all of this costs some money, and funding is not unlimited. So we should watch out for this. And all of those 4 dimensions affect the detector resolution and the effective area of the final detector. And so just to give an explanation, or like some further to underline this optimization efforts, we have here, we varied the spacing of the different lines of the detector, you know, the lines with the different modules. And we looked at the different spacings and which angular resolution we get for different neutrino energies, and the different kinds of lines is just how many PMTs there are in one of the modules which are on the lines. And as you can see, the bigger the spacing between the lines get, basically the higher the angular resolution gets, and the other way around. And you have to note, I showed you the 4 dimensions beforehand, and so improvements in one direction often negatively impact some other dimensions. So it's kind of a trade-off between the different parameters that you can optimize. Next up, I want to do some motivation why triggering especially is that important. So I've shown you this graph before, and so when we put it down there, we can connect obviously with the infrastructure that is there, but we have limits on power and bandwidth. So we somehow have to figure out that of the roughly 2.5 kilohertz expected event rate, we only detect the several orders of magnitude lower events that we are actually interested in. And for doing that, we need some real-time algorithm of some kind. And so what we are currently evaluating there is to do graph neural networks. Yeah, so this is what I'm writing at the moment. And the final plan of all of this is to then deploy it back into the ocean. So this is FPGAs. So we are currently evaluating if we just put like a big workstation in the ocean, or if we at each module or each node put actual FPGAs on which we can imprint the machine learning algorithm on a hardware level. And we have some other people working in the group on building this connection. So the algorithm and then adapting it to the power and efficiency limitations of the FPGAs, which is field programmable gate arrays, which basically means a cheap version of building your own processor, to put it like this. But it's still more efficient sometimes than having a full processor. And now I have one final overview of the full triggering algorithm. So it obviously starts with the event. That's what I said, which what the photon surrogate models do. Then there's some pre-processing. Mostly it's putting the individual timings of the photons into some histogram-like structures. So this is what you see here in those graphs. And then there's the neural network. And afterwards you get some kind of classification. The most important one here is yes or no, but what we are hoping at the moment is that we as well already at this early stage can defer some further information. For example, is it a cascade or is it a track? Or in the best case, we can as well already say, okay, it's roughly coming from this direction, or it has roughly that energy. And to be able to do all of that, we are building a digital twin. So this is, so we simulate the events, and then we do a digital version of the final detector where we over a certain period of time can really simulate how the detector behaves in its final version as close as we can approximate it right now. So we can put in some bioluminescence models, some background noise, some cascades, some starting tracks, stopping tracks, through-going tracks, events. And I have a little video how this looks like. Be aware that this is now not with the 5,000 strings, but it's just a 3-string, and it's not like big time scales, but I think it's a nice to have some overview of how this could look like. And now if I'm figuring out how to do that.
A secret corner here. So,
a secret corner. Yeah, so we play. So it's not a image film, so don't expect something super fancy. Cannot play media. Okay, so you have 3 lines here, and there's basically pop, pop. Things coming up. And yeah, so this usually moves. I can show you the video later on. And yeah, that's basically my final words for today. No, I forgot the conclusion and the next steps. So this kind of mixed me up. So I said that what we are currently working on as a group is using those machine learning algorithms, so the reconstruction at the end and the triggering algorithm to optimize our detector setup. So how we put the lines, how we build it, and that we are doing this using this digital twin method. And me specifically, I'm then working on creating a trigger algorithm. So I'm working on a trigger algorithm part and really building one that is that efficient that it can run in the ocean, in the best case on the FPGAs, and still maximize the throughput and the efficiency. And so what's next is now to obviously scale that and then do some first real application of implementing it on the FPGA, and to machine learning, optimize accuracy, try again, optimize accuracy, try again. So yeah, so that's it now. Thanks.
I think if you download the slides from Indico, I hope that it will show then on the computer this little movie.
Me too.
Yeah. Okay, so I would suggest if you have any question, Yeah, a very quick one.
So I mean, can you infer some about the backgrounds and fluorescence and such from KM3net or Antares, for instance? Because I mean, the region is not the same. I mean, so the Mediterranean Sea is not the same than this. So I mean, what about this noise?
Yeah, I mean, like those are mostly theoretical models, and as you might have guessed, it's very far away from my field. But we had like one guy working specifically on building those models, and I think he was talking to the KM3 guys, and but he was just a bioluminescence, for example. Obviously, you can do the same, but from the more specific, localized
I mean,
features.
You can learn a lot from. I mean, at least you have the even if the sea, of course, and the water is not the same. I guess that you could profit from that. I mean.
Yeah, especially when it goes to the currents of the ocean and stuff.
Nice.
Thanks.
Thank you.
Yeah, thank you very much. Let's thank Janik again and everyone in the session.